Hello everyone. Welcome to the next lecture on the PY question series. Today I will explain you how you can solve the problems related to the ring and the field theory. Myself Dr. Harish Garg. You can find me on my YouTube channel where you can find the playlist of CSIR UGC NET. In this playlist you can see the various lecture related to the class equation, calculus of variation, number theory, group theory, partial differential equation and many more available at this playlist. You can see more than 250 videos are uploaded. All are explained with the help of shortcut tricks. What we have discussed so far related to the modern algebra, we have covered the complete number theory parts with the help of the shortcut tricks and many shortcut tricks available in these two lectures related to the group theory and the class equation. You can subscribe my YouTube channel so that you can get the notification when I upload my next video. In this lecture, I will cover about the concept related to the ring and the field theory because I have received several requests from your side, so I try to prepare myself on these two topics. First of all, whenever you are on the Zn is nothing but Z by n of Z. Then the first shortcut trick is this Zn is said to be the field if and only if n is my prime. So if I say Z of 2 is a field, Z of 3 field, Z of 12 is not a field because n is not a prime. So once you know Zn is a field if and only if n is prime. Second concept, how you can find the number of the ideals of the Zn, how you can find the number of the prime ideals and how you can find the maximum ideal. For example, if I gave you the Z of 12, can you find the number of the prime ideals, number of the maximum ideal in the 10 second? If no, then definitely your reaction will be look like say this one. Very confusing. How we can find the ideals of the Z100? How you can find the ideals of the Z raised power 7? How you can find the ideals of maximum ideals of 999? I will teach you free of course how you can find the ideals, prime ideal and maximum ideals with the help of the shortcut tricks. But make sure student, you have to watch my previous lecture number theory to understand this today's lecture very well. Now, how you can find that? Very simple. The number of the ideals is my tau of n. Some books or some earlier classes is also denoted as a d of n. What is the meaning of that? Number of the divisors of n. Where and how many prime ideals and the maximum ideal, that is the w of n. You can see based on these simple tips you can look like say very happiness. How you can compute? For example, if I say n is my 12 like Z of 12, firstly you can write this 12 as a prime factorization 2 raised to power 2 into 3. Then w of n, the w means the number of the prime factors, number of the prime divisors, that's a 2 and 3, only 2. What is the tau of n? Tau of n is, if I look at the 3 raised power n, so power 2 plus 1, power 1 plus 1. So the answer will be 6. Look at the one more. If it is 8, Z of 8, then 8 I can written as a 2 raised to power cube. Then what is the W of 8? How many prime factors? That's only the 2. What is the tau of 8? Power is 3. So 3 plus 1, that is my 4. Look at one more. If you look about the 15, so n is my 15. I can write this is 3 into 5. How many prime numbers? 2 prime numbers. So W of n is my 2. What is the tau of n? So powers are my 1 and 1. So that will be 1 plus 1, 1 plus 1. So that will be 4 is the right answer of this problem. So these are the ideals of the Zn. This is the prime ideal Wn and the maximum ideal is W. For more detail about the W and the tau, you must watch about by the number theory lecture. So now, based on this concept, you can see your feeling will be look like say happiness, where tau is the number of the divisors and W is the number of the distinct prime divisors of the n. Now, how you can find the number of the maximal ideals of the Zm cross Zn? You can find the number of the maximal ideals of the Zm by using W of, and similarly you can find the maximum ideal of the Zn, and finally you can add them. Now, can you solve this problem in the 10 second? If you so, then your answer will be very good and you look like say this happiness boy. How you can solve that? Look at that. N is my 10. Write in the prime factorization 2 into 5. Fine. So what is the W of n? Because we need to find the prime ideals. So what is the W of n? How many prime factors? 2. So the right answer of this problem is 2. Can you say this is a field? Is it a field? No, because n is not a prime number. What is the maximum number of the prime? What is the maximal ideals? Again, this is the W of 10. And what is the W of 10? 2. How many ideals are there? So that will be tau of 10 and 10 I have written this form. So the powers are my 1 and 1. So that will be 1 plus 1 and 1 plus 1. So the right answer is 4. In this question, they are only talking about the prime ideal. So the right answer is 2 is the correct option. Again, they are talking about the prime ideals. Now I'm very sure that you will be look like say this. Can you solve this problem? N is 10 raised to power 5. So I can return is 2 into 5. Fine. So I can say 2 raised to power 5 into 5 raised to power 5. What will be my W of n? How many prime numbers? 2 and 5. There are the 2 prime numbers is the right. Is it a field? It's not a field. Why? Because it's not a prime number. What is the how many maximal ideals? Maximum ideal is also Wn. So the same answer. How many ideals are there? So you can see it will be the tau of n. So the tau of n will be my, from this case, the power is 5. 5 plus 1. Second power is again 5. So 5 plus 1. So 6 into 6 is 36 is the right answer. Which of the following is not a field? What I told you, Zn is a field if and only if n is prime. Now you can see that which of the one is not a field. That means not a prime. So Z4 is not a prime number. Now, this is the June 2014. Can you solve this problem in the 10 second? Look at that. They are talking about the ideals, prime ideals, maximum ideals. And I'm very, very sure that you will be look like say this when you see this question after my this video. Now, can you solve that? First of all, what is the first case is? I can return this is P square into Q. Your N will be P square into Q, where P and Q are my distinct primes. Fine. The first question is the ideals. That will be tau of N. So what will be the tau of N? It's a 2 plus 1 and power is 1 plus 1. So what will be the answer is 6. But he said 3. Look at the second option. Again the same number. Prime ideal. What is the prime ideals? W of n. How many prime numbers involvement in the P square Q? There are the 2 prime numbers P and Q, but he said 3. How many prime ideals? That's a 2, exactly to correct. Maximal ideal. Maximal ideal is my W of n again. That is again 2. But he said unique. That means 1, which is not possible. So the right answer of this problem is C is my correct answer. And you can see that how many seconds you are needed to solve the problem. I think you needed a maximum 10 seconds to calculate this problem. Don't forget to like and comment on this video as well. Can you find the maximum ideal of 27? I am very sure that your happiness will be at the extreme end, because you can see this question you can solve in 5 seconds. This is a W, 3Q, and your target is to find the maximum ideal. That will be W of n. How many prime numbers involvement in this? Only 3. So that is the answer of this problem. Very, very simple approach I have told you in my each video. Now, second concept. So you can do the practice more on the ideal, prime ideal based on your previous PY questions or your previous on your any of the books or the notes. Now, whenever you are talking about the Zn, then if you find the number of the idempotent elements, how you can find the number of the idempotent element? That will be the 2 raised to power r, where r is the distinct prime factors of the n. What is the meaning of that? That will be my W of n, number of the distinct prime factors of the n. On the other hand, if you are talking about the number of the nilpotent elements, that will be the n divided by the product of the prime numbers. For example, if I say n is my 15, so firstly you can write in the prime factorization. Fine. Then number of the nilpotent element will be n. How many prime numbers? 3 into 5, that is a 1n. If you look about the 12, you can write as a 2 square into 3. Then the number of the nilpotent elements are 12 divided by prime numbers are my 2 and 3. So the right answer of this will be 2 is the right answer. Similarly, if you look about the idempotent element, 2 raised to power number of the distinct prime factors. How many prime factors are my 2 prime factors? So 4 will be the right answer. Look at that. In Z of 8, n will be 8. The number of the nilpotent animals. The number of the nilpotent animals will be, firstly you can write in the prime factorization. Fine. So n divided by the prime number. How many prime numbers are? Only 1. So n over 2 is 4 is the right answer. You can see the cardinality is 3. Only this elements is my 4 is the right answer of this problem. Make sure this concept is only for the Zn. Now, instead of the Zn, now if you have the quotient group, if you have the quotient ring like of Q divided by F, where this symbol is used for the ideal. Fine. So we already cover how many prime ideals, maximum ideals, and other things are there. Now, how you can find the distinct ideals? How you can find the distinct prime ideals in case of the quotient ring? Fine. Remember, in case of the Zn, we define the ideals are my tau n and the prime ideals are my wn. But in case of quotient ring, how you can define that? You have to find the ideals or the distinct factors of the fx and number of the distinct irreducible factors of the fx. But there is one more method. Look at that, this example. Q is the ring of the polynomials, then the total number of the maximal ideals. This one, this is the prime ideal. So what is the total number of the maximal ideals? So you can see, if whenever you have the quotient ring of this form, x raised to power n minus 1, then the total number of the maximal ideals is tau of n. Don't confuse with the Zn. In case of the Zn, the maximal ideals are my Wn, but this is not the Z. This is my quotient ring. So the maximal ideal is my tau of n. So what is the n? If you compare them, n will be my 4. Fine. So then what will be my tau of 4? I can write the 4 is 2 square. So what is the tau is? 2 plus 1. That is my 3. So that is the right answer of this problem. Second method. Now you can see that this is the number of the distinct irreducible factors. You can see x4 minus 1. I can factorize them x4 like this manner. I can also factor them x minus 1, x plus 1, x square plus 1. So how many factors are there? 3. Again, this will be the right answer. But sometime if it is written as x raised to power 91 minus 1, then sometime it is difficult for you to write in the factorization form. So the best way is you can write in the maximal ideals. Now you can see it's a CSIR net examination for the positive integer m. Am denotes the number of the distinct prime ideals. Fine. Am is the number of the prime ideals. Again, you can see, is it a Zn? No. This is the quotient group. Fine. So what is the formula for this? Number of the distinct irreducible factor. But again, there is no need. I can again use of the tau n. So that means the answer is tau of m. Fine. Now look at the option. First option, A4. If you look about the A4, that means m is my 4. What is the answer of the tau 4? Tau 4 I can return as a 2 square. So that will be 2 plus 1, which will be 3. So first option is cancelled. A4 3, correct answer. Look at the third case, A5. So that means your target is to find the tau of 5. 5 is a prime number. So the power is my 1. So it will be 1 plus 1. That is my 2. So C is the right answer. D option is cancelled. B and D are my correct answers. How many seconds you are needed to solve the problem? a fraction of second. Moreover, in the examination, you don't need to write anything. You can do your calculation in your mind as well. Please don't forget to like, share, and comment on this video. Kindly support my efforts too, because I did my these efforts only for you in terms of the making of videos. Okay, which of the following is an irreducible factor of the x raised to power 12 minus 1? So many methods are there. First method is that's a usual calculation. You can write as a factor. It will be x6 minus 1, then x6 plus 1. Then you can again write it as a x cube minus 1, then x cube plus 1, and so on. Fine, and so on. But that is a very lengthy procedure. How you can solve this in a quick second? Can you get your answer in the 10 second? No. Again, you can see this is irreducible over the cube. So if I say if which of the following is irreducible, if I say this is my, then it will form a field. If this is my irreducible polynomial, then this will be the field. That's the quotient field. Fine, or the quotient ring. Then the maximal. Firstly, let me tell you that the highest degree of the irreducible factor of x raised to power n is phi of n. Fine. So now you can see in this case again it is the x raised to power n minus 1. So I can say what is the right answer of this? Phi of 12. What is the phi? Phi is my Euler function. So how you can do the Euler function? I can write in the prime factorization 4 into 3. So I can write this is 2 square into 3, 1 minus 1 over 2, and 1 minus second prime number. So that will be 12. It's a 1 over 2. It's a 2 over 3. That will be 4. So the maximum degree of irreducible polynomial is my 4. So 8 option cancel, 5 option cancel. Fine. Now out of these two options, now you can see that x4 plus 1 is the factor of x raised to power 12 minus 1, or x4 minus x square plus 1 is the factor of x raised to power 12 minus 1. That's the only thing. Fine. Because if this is the factor, then it is not a irreducible. If this is the factor, then it is not a irreducible. How you can check about that? It's a very simple. Assume that x raised to power plus is the factor of x12 minus 1. So what does it mean? I can say x4 will be my minus 1. That means if I use the cubing on the both side, then x12 is my minus 1. Fine. So clearly say x raised to power 12 plus 1. So that means x raised to power 4 minus 1. X raised to power 4. Can you say this is the factor? So x raised to power 4 minus 1 is not the factor. So this option is cancelled. Only this option will be the right answer of this problem. You can see x, if I assume x raised to power 4 is my minus 1, then it is x raised to power 12 is minus 1. That means x raised to power 12 plus 1 is 0, which is not true. So that means this option is not satisfied. So the right option is only third is the right answer of this problem. Okay, look at this another one. Now you are talking about the integral domain. Can you say about Zn when it is an integral domain? Can you say Z3? Can you say Z17? Can you say Z21? Which one is the integral domain of this field over the I? I think all of you know that this the I is A plus IB, iota B. Can you solve this in a quick 5 seconds? No? Don't worry. Again, I will teach you. First of all, before that, you can scan and join my WhatsApp group if you are new to my YouTube videos. This is my integral domain if and only if n is my prime number of the form 4k plus 3. Fine. For example, again you can see, again is a quotient group, is a quotient ring. Fine, is a Gaussian integers. Then which of the following is the integral domain? So look at the first option. Can you write 2 in the form of the 4k plus 3, where k is my positive integer? k is my positive integer, so definitely this is not equal to. Look at the second option, 13. Can you write this in the form of the 4k plus 1, where k is my positive integer? If so, we can find the value of this. It's a 10 over 4, which is not my integer. So that means this option is also cancelled. 19. Can you write this in the form of the 4k plus 3? That will be 16 over 4. That's a k, that's 2. K is my 4, which is a integer. Can you write the 7? So 7 is 4k plus 3. Yes, you can find the value of k. K is my 1. So yes, this is the integer, positive integer. So yes, this is also the right option. C and D are my correct answer of this problem. How you can find the number of the units of Zn? Fine. That is a phi of n. We already say how many prime ideals you can find. Fine. We already defined how many maximal ideal you can find. Now you can see how many units of the Zn. So again, the number of the units of phi 11, number of the units of phi 12. So phi of 11 is my 10. So first option is cancelled. Phi of 12 I can written as a 2 square into 3. Fine. And 2 square into 3 I can written this number is 12 into 1 over 2 into 2 over 3. That is my 4 is the right answer. So C is my correct answer. Phi of 12 I already computed them. You can see which where I have computed a phi of 12. I think I rubbed that, but phi of 12 you can easily compute them. Okay, let me do for you. Phi of 12 is 2 square into 3. Phi is a Euler function, so it's a 2 square into 3. 1 minus 1 over the first prime number, 1 minus 1 over second prime number. So can you do the calculation? It's a 12 into 1 minus half into 2 over 3. So clearly says 6 into 4 is my right answer of this problem. Now, again, this is the Gaussian integral. Find this group. That means if I say z of I, instead of the 3 minus, if I simply say a plus ib, this is the idea. This is isomorphic to what? Can you solve this in the 10 second? Again, no. Don't forget, I will teach you again the free of cost. But make sure don't forget to like and subscribe the YouTube channel. Also, make sure you have to subscribe, comment, and share this video with your friends. Now, what are the various shortcut tricks related to the Gaussian integral? Whenever you will see this field Zi over A plus IB, then this is said to be the field if and only if A square plus B square is a prime, either a prime or the prime of the form 4k plus 3. Fine. Like if I say z of I 1 plus iota, is it a field? What is the A? A is my 1, B is my 1. What is the A square plus B square? 2. 2 is my prime. So yes, this is my field. Once this is the field, is the irreducible polynomial. Second, if you calculate the number of the elements in Zi over A plus iota B, if your reaction will be again off, how you can find that? I will tell you again, it is the A square plus B square. And definitely your reaction will be just like say wow. Another thing is, whenever this ideal, that is the A plus IB, is said to be the maximal ideal if and only if A square plus B square is my prime. And this Z of I, if there is a singleton, then you can simply say Z of A, and this number is isomorphic to, if I call as Zi over A plus IB, is isomorphic to, depending upon the GCD of A and B. If the GCD is my 1, then it is isomorphic to the A square plus B square. If the GCD is not 1, then it is the isomorphic to the Z of GCD into Z of A over D square plus B over D square. Now look at that. What is the A? A is my 3. B is my 1 or minus 1. Fine. What is the GCD of this? GCD is my 1. So therefore this group is isomorphic to a square plus b square. What is the a square plus b square? It's a z of 10. So z of 10 I also written as. So the right answer of this problem is D is my correct answer. Again you can see, I think you need a maximum of the 5 seconds. Which of the following ideals is not the maximal? What is the shortcut tricks? As I told you, this ideal a plus ib is said to be the maximal. When is said to be the maximal? If and only if a square plus b square is my prime. So you can see first option is, look at the first option. What is the a and b? 1 and 1. So the a square plus b square is 2. Second option is again 2. C option 4 plus 1 5. D option is 3 9 plus 1 10. This is my not prime. If it is not prime, that means this is not maximal. So the right option is D is my right answer. Look at this another one. The number of the maximal, the number of the elements in this case. What is the shortcut tricks? As I told you, Zi over all are my Gaussian integral. The number of the elements are a square plus b square. So can you find the a square plus b square? 4 plus 1, 5 is the right answer of this problem. I hope you are enjoying this session too, but don't forget to like and comment on the video. Now, F is a field of the 8 elements such that this condition hold. That's a very simple approach. What is the shortcut tricks for you? Whenever you have the elements, say A, x belongs to the any such that x raised to power n is my 1 and x raised to power k is not 1 whenever k is lies between 0 to n. Fine. Then you can simply write the number of the elements in this set. Number of this element in this set A is my phi of n. Make sure student it must be the 1 and k must lies in between 0 to n. So first of all check whether the 1 property is satisfied. You can see x raised to power 7 is my 1. That's satisfied. X raised to power k is not equal to 1. The only we need to check whether the k lies between 0 to 7 or not. So k is less than 7. Is it greater than 0? It's a natural number. Once is a natural number, it is a greater than 0. So what is the right answer of this problem? Phi of 7. So what is the 7 is a prime number. So the right answer is 6 is the correct answer of this problem. How many seconds you are needed again based on this shortcut tricks? How many elements? Again you can see this is the same form. But if you look about that, this is given to you z raised to power 60 is my minus 1 and z raised to power k is not equal to minus 1 for 0 k is less than 60. What I told you, this must be plus 1. This must be plus 1. But in this case, it is not a plus 1. So how you can make as a plus 1? I can scare them. It is a plus 1. Then again, it is not a minus 1. I can again scaring. So it is not equal to 1. Now I need then what is your target? Your target is to prove this number should be less than of 120. Fine. So I can say I can multiply 2 on the both side. You will get this property. Fine. Now clearly say this one satisfied my this shortcut tricks. Then the number of the element will be phi of n. What is the n? N in this case is my 120. So can you find the value of the phi of 120? It will be 2 into 60. 60 will be 2 into 30. 30 will be 2 into 15. 15 is my this number. So that will be phi of 2 raised to power 3. 3 into 5. So what is the right answer of this? 2 raised to power 3. 3 into 5. 1 minus 1 over 2 first prime number. 1 minus second prime number. 1 minus third prime number. So that will be my 120. This is my half. This is my 2 over 3. This is my 4 over 5. So 5 is 15, 15, 30, 34. So the right answer is 4 into 2 into 4. So 8 4 32 is my right answer of this problem. Make sure student it must be plus 1, but it is my minus 1, so you have to change into the plus 1. Again you can see the same number z of 98, z of n, and n, this number is lies between the 98 and 0. So what is the right answer of this? Phi of 98. Phi of 98 I can written as 2 into 49. 49 is my 7 square, so that will be 2 into 7 square. 1 minus 1 over 2, 1 minus 1 over 7. So that is my 98 half 6 over 7. So that is my 14. This will be my 7. 7 into 6 is my 42 is the correct answer of this problem. Now look at this another one. Now you are talking about the field. Fine. Can you again solve this question in the 10 second? No. If you are looking about this again case, how you can solve this in the 10 second? Again, I am present for you. I will teach you again the shortcut tricks. First of all, they are talking about the number of the elements. Whenever they are talking about the field, your first thing, your first step always, you have to check about this ideal is irreducible or not. Fine. Whenever you prove that this fx is my irreducible, then you can talk about the number of the fields. Fine. Now how you can find this question in an easy manner. But before that, let me give you one message. Students, whatever the tricks I have explained to you in my each video, that will not only give you the answer in the less time, but also improve your thought process. What kind of the thought process is? How you can attempt the question in the examinations. That's the most important thing. Increasing the thought process is the most important thing. And make sure student, whenever you are watching my videos, you always watch in the positive thinking. Ignore the mistakes, always think about the positive manners. Then once you are watching the video in the positive thinking, definitely your confidence level will be very high, and you are more and more stronger to solve the problem in your exam. I hope you will remember my this tips before going to the examinations. Now, how you can solve this? Whenever you like of this question, fine. Whenever you are talking about the field and you are talking about how many number of the elements, there are the two things. Fine. First of all, when you can say is a field, if you prove that this denominator part is my irreducible. Fine. Once you prove that this is my irreducible, I think all of you know that is you can use the Einstein criteria or any of the other way. Then this quotient group, then the quotient is my field and the number of the elements is my p raised to power n. Fine. Now you can see, first of all, how you can prove is irreducible, I will tell you, but assume that this is a field, then how many elements are there, whether the 8 or 9? It's a z of 2 power polynomial, so it's a 8. So if it is a field, then it must has a 8 elements, so 9 element can never be possible. Now whether it's a field, infinite field, that's not possible because we have the 8 elements. Now the only question arises is whether it's a field or not. How you can check about the field? You can simply choose about the polynomial x cube plus x square plus 1 and check whether it's a irreducible or not. Fine. How you can check about that? Always remember, whenever you will see the 1, Einstein criteria is not fulfilled. Fine. For that case, you will look about the x plus 1 until unless this number will change to the 1 to the any other number. But you can see what is the field, what is the PID, z of 2. What is the number of the elements are there? 0 or 1. That's a finite field. So look at that. What is the f of 0? 1, which is not 0. What is the f of 1? 1 plus 1 plus 1, 3. It is concurrent to the z2. That is again 1. That is a modulus 2. So which is a non-zero. So once both numbers are non-zero, then it is a irreducible. Once this polynomial is my irreducible, therefore z2 divided by this polynomial x cube plus x square plus 1 is my field. So it's not a field cancel, and it is a field how many elements? 2 raised to power 3. That's a p raised to power n, where p is my polynomial z of p and n is my polynomial of irreducible. So the right answer of this problem is A is my right answer. Now can you say number of the elements? Clearly say x square plus 1 is my irreducible polynomials over the Z11. So therefore this will be my field. Fine. Once this will field, then the number of the elements are my p raised to power n. P is my 11, n is my degree of the polynomials, irreducible polynomial. So that will be 121 is the right answer of this problem. Look at this another one. I denotes the ideals of x4 plus x cube plus x square plus x plus 1. I call this is fx. Again, they are field, finite field out there. If it is a field, then what will be the degree of this? How many elements will be there? 2 raised to power 4. 16 elements will be there. If it is a field, then definitely 4 will be the cancel, 8 will be the cancel. Now you will, when they say infinite field, no, because you have the finite elements. So the only option left is D is my right answer. But how? Again, you can see in the Z2, the elements are my only 0 and 1. So what is my f of 0? F of 0 is my 1, which is non-zero. What is the f of 1? 5. It is again 1 over the modulus, which is non-zero. So therefore, this polynomial is my irreducible. Once it is irreducible, therefore ZF is my field. And if F is a field, how many elements are there? P raised to power n, that's a 2 raised to power 4. 16 is the right answer of the problem. Which of the following quotient rings are my field? Again, your target is to check whether it's irreducible or not. X square plus x plus 1. F3 is a finite field with the 3 elements. I can take in the Z3. Z3 is a finite field with the 3 elements. Fine. Now what is the f of 0? 1, which is non-zero. What is the f of 2? 4. 7. 7 is concurrent to 1 modulo 3. Fine. Which is again non-zero. What is the f of 1? F of 1 is 3, which is concurrent to the 0 modulus 3. So that means this polynomial is not irreducible over Z3. So once this is not irreducible, therefore F3 over this polynomial is not a field. Fine. So this option is cancelled. Now, second one, Zx over x minus 3. Now we all know Zx is not PID. Fine. So once this is not a PID, then this is not a field. Make sure whenever you want to prove this the field, this must be the irreducible, this must be the PID. So in this case, x minus 3 is Zx is not a PID, so therefore this is not right option. Now, x square plus x plus 1 and second is the qx. We all know qx is my PID. Fine. We only need to prove that this is my irreducible. Is it irreducible? How you can prove that this is irreducible? So they are not mentioned that now since it is a 1, so we can't apply the Einstein criteria. I can shift them, say x plus 1. So that will be x plus 1 whole square, x plus 1 plus 1. So clearly say if you open them x square plus 2 plus 1 3, 2 1 plus 1 plus 1 3. So clearly say if I choose the prime number 3, then clearly say 3 divides the constant, 3 divides the coefficient of the x, and 3 doesn't divide the leading coefficients. Also 3 square doesn't divide the constant. Remember always whenever you have a polynomial of this nature xn minus 1 plus up to the an, then if you choose a prime number p which divides the a0, which divides a1, which divides an minus 1, but P doesn't divides AN. Also, P square doesn't divides A naught. Then you can say this polynomial is my irreducible by the Einstein criteria. Now you can see f of x plus 1 is my irreducible. This implies fx is also irreducible. This is my PID. This is my irreducible. Yes, this is my field. Now look at the last option. F2 divided by x square plus x plus 1. F2 is a field with the two elements. I can choose Z2. Fine. So clearly say Z2 is my PID. Fine. Now we will see whether it's irreducible or not. What is f of 0? 1, which is non-zero. What is f of 1? 3. 3 modulus 2 is 1, which is again non-zero. So therefore this is my irreducible. Hence this is my field. C and D are my correct answer of this problem. I1 is the ideal generated by x4 plus 3x square plus 2 called as F1. F2, that's ideal I2 is generated by this. Which of the following are the field? Clearly say Q is my PID. The only need to check whether they are my irreducible or not. So clearly say I can factorize them x square plus 4. So once you can factor them, it is not irreducible. Once this is not irreducible, that means the first one f1, this is f1 f2, this is basically f1. That means capital F1 is not field. Similarly, you can see x plus 1, it is x square minus x plus 1, and clearly say the roots are in the Q. So that means this is again not irreducible. That means this is my reducible polynomial. So again you can see F2 is not field. So neither the F1 nor F2 is the field. P1 and P2 are the ideals generated by this. Then again a very simple. You can see F is my x cube plus x square plus x plus 1. Can you factor them? I can take x square common. Then your factor will be this number g x cube minus x square plus x minus 1. Again you can see x minus 1, x square plus 1 is the fine. Then the sum of the two ideals. This is my ideal. If you add them, which one is the common factor? Can you say about the common factor? X square plus 1 is the common factor. That is the right answer of this problem. Fine. Otherwise, another way is, what is the definition of f plus g? That will be pick the element of the f into some polynomial plus pick the element of the g into some polynomials. That is where f and g are my polynomials. Now these are the elements. If you multiply this element by polynomial px, multiply this element by the polynomial qx, and if you add them, clearly say x square plus 1 will be common. Inside one is again the sum polynomial. So that polynomial is my x square plus 1 is the right answer. I1 is the ideal generated by x square plus 1. I2 is the ideal generated by x cube minus x square plus x minus 1. Clearly say I can factorize them. X square plus 1, x minus 1. So clearly say this is my not irreducible. Fine. X square plus 1. If you factorize them, x plus iota, x minus iota. But my field is q of x. So that means this number f is my irreducible over q. So once f is irreducible, that is I1 is irreducible, R1 is my field. This is not irreducible, R2 is not field. Fine. So R1 and R2 are field, R1 is a field, R2 is not a field. Now, fine. Now, how you can prove the integral domain? Since R1 is a field, that implies R1 is my integral domain. Fine. So R1 is not an integral domain, cancel. R1 is the integral domain. Now we will see whether R2 is the integral domain or not. Now we all know QX is my PID, fine, and this is my I2. I2 is my not a irreducible, that means it's not a maximal ideal, or you can say it's not a prime ideal, fine. Once it is not a prime ideal, that is R2 is not integral domain. So R2 is not the integral domain, correct? B and C are the right option of this problem. Now, another shortcut tricks, whenever you have the field F, if you want to find the number of the subfield, how you can find the number of the unique subfield? Again, if your reaction is look like say very confusing, again I will tell you this is again my tau of n, and it's a subfield look like a subring subgroup whenever you have to define the order of p raised to power m where m divides the n. And I'm sure that based on these shortcut tricks your reaction will be look like say this one, and you can solve each problem with the 10-second time period. How? Remember that this is a tau of n, tau of power, prime of the power. You can see number of the subfield. What is the n? Is a prime. So the answer is tau of 100. So can you write the 100? It's a 4 into 25. 4 into 25. What is the tau of this? So that's a 2 plus 1. 2 plus 1. So 3 into 3 is the 9 is the right answer. Again 10 seconds you are needed maximum to solve the problem. Number of the subfield of 97. Check whether 97 is a prime or not. Yes, so you can see tau of 97. This is a power. Fine. So since 97 is a prime number, so 1. So what is the tau of 1 is 1 plus 1. That's the 2 is my right answer. Number of the subfield of order 43 raised to power 144. Clearly say 43 is my prime number. So the right answer is tau of 144. It's a 12 square. 12 I can written as a 2 square. 12 I can written as a 2 square into 3. So it's a 2 raised to power 4, 3 raised to power 2. Can you find the tau of this? 4 plus 1. Second power is 2 plus 1. So that is a 5 into 3. 15 is the right answer of this problem. Let P is the prime number. How many distinct subring with the unity of the f of p square? That is, order is my p square. It's a prime. So the tau of 2. What is the tau of 2? Power is 1. So 1 plus 1, 2. So you have the 2 subrings. That means one is the fp, second is the itself fp square. Question arises is cardinality p. How many cardinality of the p? Only 1. So the right answer of this problem is 1 is the right answer of this problem. Let G denotes the group of all the automorphisms of the order 3 raised to power 100. Then the number of the distinct subgroup of this. Again the same quantity, same formula. Tau of 100. It's a p raised to power n. Number of the distinct subgroup. 100 I can written as a 4 into 25. So that will be 2 plus 1, 2 plus 1. So 3 into 3, 9 is the right answer of this problem. Please don't forget to like, share and comment on this video. Also subscribe my YouTube channel for the get notifications. Okay, now you can see, can you find the degree of the extensions? That is the extension field. Can you write this answer in the 10 second? If you look like say like a very cry or very confusing, don't worry. I will tell you again, my rule is changed from the oof to the wow. I will tell you how you can find the degree of the extensions like of k degree f. Fine. So how you can do that in a very simple manner. First of all, whenever you are look about this case k of l or f of this, it is always the degree of the minimal polynomials. But the question arises is how you can find the degree of minimal polynomials. So that I will tell you. Look at that. The first case. If you look about this case, if I write you again root of p1 root of P2 and root of Pn. Find quotient group of this. The first way is you can you can find the minimal polynomial and then you can find the degree, but there is no need. Where P, remember that Pi's are my primes, are my distinct primes. Fine. Pi's are my prime. So what is the power? This is my 2. How many square roots are there? N. So the answer is 2 raised to power n. Fine. Similarly, if you look for the second case, it will be my cube of P1, cube of P2, and so on, cube of Pn, degree n. So can you find the degree of this? So it's a power 3. How many P primes are there? N. So the answer is 3 raised to power n. Fine. Now, if it is not visible, I can write for you again. It's this quantity. Now, look at the second case. Now, in this case, here is only q, but right now it is written in some another form. So, what is the answer of this case? It's a 2. How many? N. Because it is after the quotient, it is divided by 2 because the power is my 2. It's a m. So, it's a 2 raised to power m. I can say 2 raised to power n minus m is the minimal polynomial degree. Similarly, if you look about this case, it's a P1 up to 3 times of the Pn, quotient of Q, cube of P1 and cube of Pm. So can you tell me the answer? It will be cube 3 raised to power n divided by 3 raised to power m. That will be 3 raised to power n minus m. Fine. Similarly, if you look about this case, instead of this, now I have written combined form like P1, then Pn, comma, cube root of Q1, cube root of Qm, colon, Q. How you can find the degree of the minimal polynomial? Make sure that P and Q are my distinct prime. So you can think about this is the one quantity. What is the square root? 2. How many times? N times. Because this is written inside it, so it's the cube root, multiply it how many times? M times. Because there is no other term involved, so the right answer is 2 raised to power m, 2 raised to power n, 3 raised to power n. Similarly, now if it is written also on this side, so that will be how many times? 2 is the n times. It is cube root of m times divided by 2 of r times, and this is the cube root of s times is the right answer of this problem. So based on this, you can find the degree of the minimal polynomials. For example, whenever if somebody is write like this way, root 2 comma iota, or if somebody simply write as a omega, then always treat I and omega as a square root of p. It is basically a cube root of p. So can you find the degree of this? Because it's a 2, only the one prime number, it's a 2 raised to power 1. Can you find this? This iota I can written as a root of the prime number. So it will be 2. How many numbers are there? 2. So it's a 2 raised to power 2. 4 is the degree of the polynomial. Also make sure instead of writing this as root of p1 comma root of p2 comma this, instead of the comma you can written either as a plus sign or minus sign. This is the same quantity. This is also p1 plus p2. So what is the answer of this? If both are the square root, how many numbers? 2 numbers. So it's a 2 raised to power 2. 4 is the right answer of this degree. You can see your target in the first case, your target is to find q root 2 plus root 3 and q of root 2. Fine. So can you write the answer in the quick second? So the answer of this case, both are the square root. How many times? 2 times. Because it's my quotient divided by how many prime numbers? Only one number. So 2 raised to power 2 divided by 2. So the degree is my 2. Can you find this? This omega, I can written this as root 2 and any of the prime, but 2 must be different from it is my of prime. So what is the right answer of this? So this part is again 4. This part is 2. So 4 divided by 2 is again degree 2. Can you find this? Degree is my 2 into 2, 4 divided by 2. So that is again 2. Can you find this iota? Iota I can again written as a root of p. So 2 into 2, 4 divided by 2. So the answer is 2. 4 divided by 2 is a 2. Now you can see it's a cube root of 2 omega. Omega I can written as a root of p quotient of omega prime of the 2. Fine. In this case, p is different from the 2. So what is the answer of this? Is a cube root. How many cube roots are there? Only one. Square root. How many square roots are there? Only one. Divided by square root of 1. That will be 3 is the right answer. Whether you have written the plus sign or you can written as a comma, that's both have the same meaning. So how many square roots are there? 2 divided by 2 raised to power 1. It's a root of 2. So root is appeared 2 times divided by 2. Again 2. It's a cube root. So 2 is written as a 1 times. Cube root is written as a 1 times divided by 2. So the answer is 3 is the degree of the minimal polynomial. Now look at this one. Can you find this degree of root 2 root 3 over q? So what is the degree of this? There are the written square root. How many times? 2 times. Both are my distinct prime because there is no number written, so you have nothing divided. So that's a 4 is the right answer. Now can you solve this question? So what is the degree of this? It's a 2 raised to power 1. It's a cube. 3 raised to power 1 over this number divided by square root of. So that will be 3 is the right answer. Find the algebraic field of E over Q. That means E root 2 root 3 root 5 over Q. Fine. So now you can see again all are my square root. How many times square root? 3 times. And there is no other term. So that's a 2 raised to power 3. 8 is my right answer. Make sure student this number must be different. Distinct prime numbers are there. That omega is the complex number such that omega cube is 1. L is a field generated by Q cube root of 2 omega. Omega I can written as a prime P over the field of the Q. Then the number of the subfield. Now they are talking about the subfield. What is the subfield? I have told you tau of n, where n is the order of the p raised to power n. So firstly you can find the order of this degree of the minimal polynomial. So it's a cube root 1 square root 1, that is a 6. Fine. So that means your target is to find the value of tau of power. So 6 I can written as 2 raised to power 1, 3 raised to power 1. So what is the tau of 6? 1 plus 1 and 1 plus 1. 2 plus 2, 4 is the right answer of this problem. The degree of the extension Q, I can write the largest power first, fourth, and this over Q. Now, you can't say that it's a 8, 1 times 4 is a 1 times 2 is 1 times is the right answer because these are my not distinct number. Fine. So once it's not a distinct number, you can write this as a opening form. That's first quantity 4 this quantity raised into Q of 2. Find first part into Q of 4 root 2 into Q of root 2 into Q of root 2 into Q of root 2. Fine. Clear? Then how you can write this? So it will be, they are the same. So the degree is 8 by 4, 2, 2, 4 by 2 and 2. That will be 8 is the right answer of this problem. Now you can see the number of the this is the shortcut tricks for you. Whenever you are working in the ZP, then P is my prime, then the number of the irreducibles are my P minus 1 over 2 of the this form. While whenever you are talking about the reducible polynomials, that is a P into P plus 1 over 2. Now remember students, you always believe in yourself that you are the best students, and once me and you both can learn through the single platform, then definitely you can do it easily. Once you are more comfortable in solving the problem in your examinations, then your result will be always happiness, and you will get success in your examination in a very simple manner. So this is simple. Oh, one second. This is, I think, wrongly written. This is only Q because we have to reach at the point Q only. So this is only Q. So that is my, again, it's a degree is my 2 divided by 1. It's a 2 and it's a 8 is the right answer. Now based on single this word I can close this lecture, and I hope you have learned many shortcut tricks through this part. Best of luck students. Happy luck. Thank you very much.